Good day and welcome back for the first part of our discussion on linear approximation. For this topic, we are going to take an old familiar idea to us, tangent lines, and we're going to give them a new spin. And the motivation for this topic is going to come from the picture that we have to the left. The idea in this picture is that I have some curve in purple, which we're thinking of as being the graph of a function f of x, and the dashed blue line is going to represent the tangent line to this curve f of x at x equals a. And what I want to observe is that if I imagined zooming up, maybe looking through binoculars or a microscope as to what is going on around that point of tangency. When we blow that up, what's going to happen is we have the curve itself, and then at that point of tangency, I want to note as you get closer and closer to it, they're almost indistinguishable from each other. And the idea is going to be that maybe the function f of x, for whatever reason, is difficult to work with. Even if the function is difficult to work with, a tangent line is just a line. So for example, if we would like to know something about the function value at a point close to a, so let's think about this as x naught, if we go up to the curve, it may be that the function itself is difficult to approximate or evaluate at x naught, but we could substitute that into the tangent line and hopefully very quickly get an idea of the function value there. So the idea is summarized below. For x naught close to a, we can use the tangent line to the curve f of x at x equals a to approximate the function value at x naught, where x naught is something close to a. That is to say, f of x naught, the function value that we might want to approximate, can be approximated by the tangent line. And note, all I'm going to do here is just give it a new name. I'm going to let L of x represent the tangent line to the curve, y equals f of x, at x equals a. And this is the entire idea behind linear approximation. In fact, L, the name I've given the tangent line, stands for linear approximation. And in order to be a bit more formal, let me just state this as a definition. The linear approximation of a function at x equals a is defined as follows. We define it to be L of x is equal to f prime of a, x minus a, plus f of a. And note what we have on the right. This is nothing more than the tangent line to the curve given by f of x at x equals a. This old familiar calculus idea that we introduced back at the beginning of the course. And what we are doing by calling it L of x is more or less just giving it a new name. We're kind of repackaging how we are using it. So let's look at a very common but still familiar example. We've been asked similar questions throughout the semester. Now I'm just going to ask it with a bit of different language. Find the linear approximation of the function 1 plus sine x at x equals 0. Previously, what you would have asked you to find the equation of the tangent line to the curve at x equals 0. So let's just go ahead and note, as usual before doing any work, what it is that we are looking for. So L of x is going to be f prime of 0, x minus 0, plus f of 0. And the 0 coming from the fact that it is the linear approximation at x equals 0. So as usual, we see that there are two function values we need, f of 0 along with f prime of 0. And doing a little bit of work to the side, f of x is 1 plus sine x. So f of 0 is 1 plus sine 0. And sine of 0 is a common trigonometric value, 0. So we've determined the first of the two function values we needed to find. And note, we are typically going to be using the linear approximation at a point where the function is easy to evaluate. That is to say, f of a, or in our case f of 0, is a familiar value or a straightforward computation. Let's move on and calculate the derivative. And what I would like you to do at this point is to pause the video and finish up the computations to determine this linear approximation. Hopefully now you have done so, but let's go ahead and fill in those details. Differentiating term by term, the derivative of the constant 1 is 0, and the derivative of sine is cosine. F prime of 0 is cosine 0, which is a common value. Note, cosine of 0 is the number 1, which is the other value we are hoping to determine. So our linear approximation, i.e. tangent line, is given by 1 times x minus 0 plus 1, or we might write it even more conveniently as simply x plus 1. And to help with the graphical intuition, we can see this above. The red dashed line is our linear approximation, so we're thinking of this as being L of x is x plus 1, and in black we have the curve given by 1 plus sine x. And once again, I want to go to that general bit of intuition. If we really kind of zoom in around this point of tangency, which I'm going to try to do here, we should note that as we get closer and closer to that point of tangency, you can really see here that the curve and the tangent line become almost indistinguishable from each other. So let me zoom this back out so that we have something we can focus in on. So we're claiming that this tangent line is going to give a good approximation to the curve for values close to 0, where we have found the tangent line. And we should be able to verify this claim just by evaluating the function in the tangent line close to 0 and comparing their values. So for example, in this table, we're thinking for substituting in values of x close to 0 on either side, what will the function outputs for f of x be and L of x? Now, note they both have that point 0, 1 in common. So when we substitute in x equals 0 to both of these curves, we will get out the value of 1. And if we just work our way from left to right and we substitute in these x values for f, we would get 0.521, 0.9002, 0.99000002. And you could easily check this by substituting those values into your calculator. And then lastly, when we substitute in x equals 0.5, we get 1.479. When it comes to looking at the equation of a line, like say 1 plus x, it is much simpler to substitute in those values of x. If x is 0.5, we get out 0.5. If x is 0.1, we get out 0.9. If it's minus 0.01, we get out 0.99, and so on. And the only observation I want to make is that our previous claim of being able to use that linear approximation to approximate values of the function when we're close to 0, we can really see that's true in our table, especially if we focus in on being close to 0, though it's actually kind of true even when we get further away from 0, depending upon the level of accuracy we would like to see. And this completes our introduction into the ideas behind linear approximation. In our next video, we'll further explore how we can use this idea to approximate function values. So stay tuned and take care.